Let's solve a problem that exemplifies Hooke's law, the relationship between the force that a spring exerts on an object and how far the spring is stretched or compressed. All right, so this is just an example of something that goes on in your kitchen. You take a mass and you just put it on top of a spring scale. And what's going to happen is that spring scale is going to compress a little bit, and the little gauge is going to give you some reading telling you how massive the object is. Okay, so what this question is asking us is for an object of known mass, how far will that spring compress? How many centimeters down is this going to move down when it comes to rest? All right, so if we just define our coordinate system to be positive pointing upward, just visually, let's form an expectation. When you put the mass on the scale, it's going to go down. So you ought to expect the value to be negative. And what we'll see is that we do indeed prove that at the end of the problem. So we expect a compression to be negative because we're defining up to be positive. Okay, so let's just begin by drawing the free body diagram of the mass that we're putting on the scale. Well, this relies on the Earth, so there's going to be the gravitational force due to the Earth. And then this is the new wrinkle. The spring force is going to be directed upward. So the spring inside of the scale here is going to be applying a force upward on the mass. And that's going to counteract gravity exactly, because just picture what's happening when you put this mass on the scale. It's going to go down, and then it's just going to come to rest. And that's the point that we're talking about. Okay, so this is our complete free body diagram right there. And then from this point, all we do is take that free body diagram, and the way we've done so many times, just insert that into Newton's second law. And so we're just going to take these forces off of our free body diagram and put in the spring force and the gravitational force right there, just as vectors. And then let's address the acceleration of this when the mass is doing what you see it doing on the scale right there. The scale has compressed some amount, and then the mass comes to rest. That's the point that we're talking about. Its acceleration is equal to 0 at that point. So what we can determine is that the net force acting on the mass at that point must be equal to 0 newtons. Okay, so the right side of our expression is equal to 0. Well, let's take these two vectors, take them out of vector form, put them into magnitude form. On our free body diagram, Fs is pointing upward, so we just make that positive. Fg is pointing downward, so we make Fg negative. And again, that's equal to 0. Okay, let's just move Fg to the other side. That's going to give us this expression right here. The spring force magnitude is equal to the gravitational force magnitude. Okay, so here's another new wrinkle. How do we express the spring force magnitude? Well, here's our expression for Hooke's law up here. The magnitude of the spring force is the negative of the stretchiness of the spring. That's going to be our 60 newtons per meters. All that means is if you apply 60 newtons of force to this spring, it will stretch 1 meter. That's what that's telling you. And then delta S is the variable that we're ultimately solving for, how far the spring has stretched or compressed. Okay, so all we've done is take this expression, plug it in right there for Fs. We've done what we've seen many times. Fg is just the mass of the mass multiplied by the acceleration of Earth's gravity. Okay, all right. The next step is we want to isolate delta S, so that's what we've done here. All we've done is move the negative delta K to the other side, to the right side of this expression, and that gives us this right here. Okay, so next step is all we have to do is just plug numbers in. That's this step right here. What you end up with is negative. The numbers give you 0.04. The units work out such that a kilogram meter per second squared gives us newtons in the numerator, and the K constant, the stretchiness of the spring, has units of newtons divided by a meter. So how that works out is we end up with negative 0.04 meters. So we should find some reassurance in that we were seeking a distance and we got units of meters, so that's good. And we also got the negative sign that we expected. Why did we expect that? Well, just a reminder, if the equilibrium position was somewhere up here when you put the mass on the scale and it went down to there, then delta S is going to be that right there. And that's what we've measured. So you'd expect that to be negative. And that's what we got.